Good morning. I'll formulate the result we obtained in the previous lesson. So let
Recording in progress.
the functions a, s, x and b, s, x are given for s, x and the product, the interval 0t and RB. We suppose that this is RD valued functions and the values of this function are symmetric, positive definite operators in RD, and suppose that all the assumptions of the theorem are fulfilled. That theorem that asserts that there exists a fundamental solution to the corresponding parabolic equation. Okay, so BSX is such operator, then this is not less than C1 theta square, C2 theta square for all theta from RD and all SX from that set, where C1 is positive and C2 is not less than C1. And the function BSX is Hilbert continuous in both its arguments. The function ASX is continuous bounded and Hilbert continuous in the space argument. Okay, and we show that on the space of continuous function of all continuous functions defined on this interval with their values in RD, we consider the sigma algebras MST, then this transition probability density generates a family of the probability measures PSX. They are given on MST, and this measure is such that the process Cs of t defined by the following equality: x of t minus x of s minus integral over the interval from s to t a tau x of tau d tau. This process is an MST PSX martingale. Martingale. With respect to any measure, PSX. Okay? S is fixed and it is a martingale in T. And this martingale is square integrable and the following process Cs of T theta squared minus integral from S to T B S B tau X of tau theta B tau. This process for fixed S is also MST PSX martingale. In the theory of martingales, the following terms are used. They say that this process is a square integrable martingale and its characteristic is given by this integral E tau x of tau d tau. Cs of T is a vector valued martingale and its characteristic is an operator or matrix. Okay? And now it is well known that we can consider stochastic integrals with respect to this martingale. Let us consider the following integral from S to T. S is fixed in these considerations. S is fixed. S is some point from this interval near T. Okay, so let us consider the following stochastic integral with respect to that martingale. B tau x tau B S X is uniformly non-degenerated operator, positive definite, so there exists its inverse operator, so, and it is also non-degenerated, bounded function, okay? and it is positive definite, so I can consider square root of b minus 1. Okay? It is well known how to. It is well known that this is also a square integrable martingale, and how to calculate its characteristic, square characteristic. It is equal b tau x of tau minus 1/2 and characteristic and square root of characteristic of psi s. Okay, so psi s of tau to the power 1/2 the tau. Now, let us write down this in the following d psi s t tau. And I am sorry, and I have write down here square of this. Square is equal to -1. Okay. And what is it? B minus 1. B, this is an identity operator times t minus s. So this is a continuous martingale. It is square integrable, and it is such that if I subtract from square of this martingale, I receive, if I subtract this process, I have 0. So this is a square characteristic of this process. Let us denote it by Ws of t. So Ws of t is a martingale, square integrable, and its characteristic is this process. And there is theorem, Levy theorem, that asserts that this process is nothing else but Brownian motion. Brownian motion, that is such a diffusion for which Sx is identically 0 and Bsx is identity operator. And now we can conclude from these formulas that Cs of t is also a stochastic integral b 1/2 d tau x of tau to the power 1/2 d xi dw s of tau dws of tau. So you see, this is a stochastic integral with respect to Brownian motion. Therefore, we can write down this equality as in the following form: x of t is equal x of s plus integral from s to t a tau x of tau d tau plus integral b tau x of tau to the power 1/2 dw s of tau. Ws of tau is a vector valued process, okay? And this is operator. So this stochastic integral is well defined. So you see, in the previous lesson, we obtained the following result: that process that constructed with the help of fundamental solution is a solution to the following stochastic differential equation. And this is a weak solution because we reconstruct this Wiener process. If you have a strong solution, then you have coefficients and a Brownian motion, and then you construct solution as a function of that Brownian motion. And now, and here we have something the other, because we construct a measure on the space of continuous function in such a way that this process is a stochastic integral with respect to a Brownian motion that we construct. Okay? And this is the so-called weak solution to this stochastic differential equation. Okay. In 1969, two American mathematicians, mathematicians struck and paradigm. To pose the following problem. Suppose that we have this space of all continuous functions. They consider it unbounded. Time was an unbounded semi-axis, and the values of those functions for the space are D, in the same sense MST, MS, and let the coefficients ASX and BSX be given. Now SX is a point from this product. ASX is RD valued and BSX is the values of BSX are symmetric positive definite operators, and they ask under which conditions on these functions there exists here a measure PSX given on this sigma algebra for all S and X. And that measure is such that the process CS of T being equal X of T minus X of S minus integral A tau X of tau tau. This process is square integrable martingale with respect to that unknown measure, yes? And this martingale is such that its square characteristic is given by the integral b tau x of tau dw d tau, sorry, d tau. And I formulate a particular case of their general result. It sounds, this is a theorem, stroke and Varadan. (1969).
Excuse me. This integral, the last one, from S to T, right?
From S to T, yes, yes. Thank you. Sorry. And the result, a particular case of the result, I formulate here. If BSX this function. Is bounded, and uniformly continuous. Uniformly continuous. And if BSX theta is strictly positive for theta being other than 0. Theta is an arbitrary vector from Rd. Okay, and about the function a as x, the assumption was as follows. This function must be measurable, and bounded. Under this assumption, and under these assumptions, the process, there exists a unique measure PSX on this space, such that this process is a martingale with respect to this measure and filtration MST. Okay, and that martingale is a square integrable one, and its square characteristic is equal to this integral. This result is very strong because you see we have here assumptions. It must be held continuous, okay, and it is uniformly non-degenerated, okay. And here we have only uniform continuity of this function. Yes, and it must be bounded, and it is non-degenerated at any point Sx, but maybe, okay. And now a question arises. Suppose that we have this situation, so there exists a Markov process in our new sense, in Dynkin's sense, that there are x of t functions, there is filtration, and there exists a unique measure, PSX, such that this is a martingale square integrable, and its square characteristic is given by this integral. And I would like to ask you, is this process in the Struve-Paradan theorem diffusion in Kolmogorov sense or not? I think that you can answer this question. And the answer is generally speaking, this process is not the diffusion in Kolmogorov's sense. Why? Because you see, the integral from S to T y minus x p s x t dy is equal to integral from s to t d tau integral a tau x of tau d tau, excuse me, a tau of y p s x tau dy. Just because this process is integral, therefore its expectation is equal to 0. And this means that this integral coincides with this one. And if Asx, if the function Asx is continuous, then we can assert that this integral divided by t minus s goes to Asx. Okay, if t goes to s. If t goes to s, because this function is continuous, and our process is the trajectory of our process are continuous. So you can expect that this is the limit of these integrals as t goes to s is Sx at any point, at any instant of time s, and at any point x in org. But you see, they constructed such a process under the assumption that Asx is only a measurable bounded function. So if a tau y is not continuous at the point x, one can hardly expect that limit exists and is equal to Asx at any point x. Okay, and in the definition of Kolmogorov's diffusion, in the sense of Kolmogorov, this limit must exist for any s and any x. So you see, if this is a diffusion, then it is not in Kolmogorov's sense. Term diffusion process is used in many books in different sense. Sometimes one says that the solution of this, a solution to this stochastic differential equation is diffusion by the definition. Okay? And I am going to construct in my future lessons, I am going to construct some diffusion in a new sense with locally unbounded function, or maybe even it may be a generalized function. Okay. So I would like to tell you that there is a book by these authors. It was published in 1979. And its title is multidimensional diffusion. Process. This publishing house. Okay. Now I would like to speak about the following things. The Hellman-Katz formula. So we now consider a general Markov process. I denote it by xt, mst, psx. This is a Markov process in the phase space X B. And the problem that we now will consider is the following. Suppose that we have some function v as x on the space and suppose that this function is such that such an integral is well defined. The problem is how to find out the distribution of this. This is a functional of our process. You see, this is a trajectory of our process. I substitute it into this function and integrate, and this is a functional of our process. How to find its distribution? Now let us make a little break. Let us continue our considerations. So the problem is to find out the distribution of this function. Some assumptions about the process and this function should be made, and the first one, the trajectory must be such that this integral is well defined. So if this is a measurable function as a function of both arguments, okay, so if I substitute here the trajectory, it must be a measurable function as a function of tau. Okay, and the integral must be well defined. Okay, so we suppose that our process has the following property. If I consider the trajectory of our process and consider it as the mapping from this measurable space. Into xb. And we suppose that for any s and t, this is a measurable mapping. That will be true if x is, for example, a continuous function, or x of t for fixed omega is continuous, right continuous function without discontinuities of the second kind. Okay? Sometimes the processes with this property are called progressively measurable. Progressively measurable. So, if v tau, vsx is a measurable function, then this integral and v, for example, a bounded function, then this integral is well defined, and moreover, we can assert that it is MST measurable random variable. Okay? So, if we would like to find out the distribution of this random variable, so we have to find out the following characteristic function. Okay, if we find out this function, we will have some information about the distribution of this integral. And now let us consider some more general situations. Suppose that we have some function v, and I would like to consider the following indicator of gamma, x of t. Exp integral v tau x of tau b tau.
Excuse me?
where gamma is a measurable subset of in phase space.
I think lambda is from R, not from RG.
Oh yes. Thank you. Thank you. I'm sorry. We can consider vector value then, but it is it. Okay. So this expectation is well defined if expectation of x exists. If V is a complex valued function like this, so this absolute value is equal to 1, so such an expectation exists. But if V is a real valued function, so this expectation exponential V minus tau x tau d tau is less than 1. Okay? And so we have consider only the situation when V is positive, not negative. And let us ask ourselves when, for which V, this expectation is finite. Vs(x) is non-negative function. Of course, if V is a bounded function, it is evident. But sometimes unbounded functions should be considered. And so I would like to prove some proposition. Let Vs(x) let the function Vs(x) be given with its values with non-negative values. and let the process satisfies let the Markov process and let a Markov process satisfies that condition. Maybe I write down here Markov is B and let a Markov process X T M S T P S X be progressively measurable. If the following condition is fulfilled, integral, the tau integral over x v tau y p s x tau dy supremum over all x from x and supremum over supremum over S from T minus H T and supremum over all T on a finite interval if this supremum H here is a positive, okay? T okay, if the limit of this is less than 1, then expectation of the expectation of exponential from S to T V S V tau X of tau V tau is finite for all T S T how to prove this assertion? So suppose that I would like to say the other way. From this assumption, follows the following. There exists for any q less than 1, there exists for any q less than 1, there exists H0 positive such that integral from s to t d tau integral over all x v tau y p s x tau dy is less than q, less than or equal to q, if t minus s less than h0 and s and t we fix some t capital and consider our consideration will be on this interval 0 t capital. Okay, so this assumption implies that for any q less than 1, not for any, yes, if this limit is some number, so there exists
So there exists such q.
there exists such a q, q less than 1, and H0 positive, such that, okay, and now we can write down this exponent as the sum. So we choose s and t such that t minus s is less than this h0, and they are on this interval 0 t capital. Okay, so I write down that exponent as the sum. One over n factorial integral v tau x of tau d tau to the power n, and consider the integral as expectation as x integral
Recording in progress.
tau x tau d tau to the power two to the power 2. Okay, it can be written as 1/2. It follows 1/2 integral v tau x tau integral from tau to t v tau prime x tau prime d tau prime d tau. Okay, and I can calculate this expectation. You see, this is equal to the following expression: 1/2 expectation excuse me, not 1/2. 2, right? Yes, 2. We integrate this, we receive this integral squared over 2. So we have here 2 integral from s to t v tau x of tau expectation tau x of tau integral from tau to t v tau prime x of tau prime d tau prime d tau. But if t minus s is less than h0, then here t minus tau is also less than h0. So this expectation is like this from tau to t. Okay, and it is less than q. V is non-negative function. So this is less than q, and so we have that it can be estimated as 2q squared. And now, by induction, we can assert that this expectation not greater than q to the power n over n factorial q to the power n. So then the expectation exponent integral v tau x of tau d tau, then not greater than the sum from 0 over all n from 0 to infinity q to the power n 1 over 1 minus q. So this is finite. This expectation is finite, okay? So if we can make this integral being less than some number less than 1, uniformly with respect to x and st over a finite interval. So we can assert then that expectation of this exponent is finite. In the general case, we should divide our interval by some points such that the length of each one of these intervals are less than h0, and then we can use the Markov property, and you see this proposition is true. Okay, and now let us consider some example. Let example. Let our process be Brownian motion. Brownian motion. Energy. So its transition probability density with respect to the back measure in algae is given by the following function: gsx t y is equal to 2 pi t minus s to the power g over 2 x minus norm y minus x squared over 2t minus s. Okay, and let us consider integral the tau integral over rd g s x tau y v tau y dy, and let us v is non-negative. Okay, let us apply the Hilder inequality. So we have here integral the tau integral over rd v tau y to the power p dy to the power 1 minus p integral over the interval integral over rd g s x tau y to the power p over p minus 1 and dy okay, p minus 1 over p. And we should estimate when this integral is finite. So t minus s to the power, excuse me, I forgot to write down minus, okay? I'm sorry, minus d over 2. Okay, so we have d minus s, tau minus s to the power minus d over 2 times p over p minus 1. Okay? Integral over the integral d tau. Okay, and the integral of this exponent gives us t minus s to the power plus d over 2 d tau. And then we have to write down p minus 1 over p. And when this integral is finite, let us calculate d over 2, 1 minus p over p minus 1. This is equal to minus d over 2 p minus 1. And this integral is finite is if the number d over 2 p minus 1 is less than 1. Or p is greater than d over 2 plus 1. Okay? P plus 1. So if our function b is such that this norm is finite, okay, then we have that this estimation goes to 0 as t minus s goes to 0. And in proposition, we have the condition that this limit must be less than 1. 0 is less than 1, okay? So the function b must be unbounded, locally unbounded, okay? And that condition in proposition is fulfilled. Okay. So now we suppose that we function v is such that expectation exponent integral from x to t v tau x of tau d tau is finite for any s t and x. Okay, and we introduce the following maybe complex valued function, okay? Denoted by P, V, S, X, T, gamma. An exercise for you. Prove that this function satisfies the Kolmogorov-Chapman equation. It may be a complex valued function, yes, if V is, but it satisfies the Kolmogorov-Chapman equation. And next time we write down some equations for this transition, not transition probability, because it is not a probability measure. Generally speaking, it is not a probability measure with respect to this argument, gamma. But it satisfies the Kolmogorov-Chapman equation. Okay, that's all for now, for today. See you next Tuesday. Bye.
Recording stopped.